that they did.
Like, I literally didn't finish this, I only finished one test.
Well, it depends on what it is, because it averages all the subjects.
If I'm like,
So it wouldn't matter.
I don't know, but like my science, I
don't
only
really
had
crash
passed it.
there.
Okay. Alright.
The timing is like, okay, I asked
It's
about
not-
science, but yet that's not saying.
I don't know, we have nerve.
It's not like
Kramer.
you
Oh.
have to get
Because one time I did,
20 or
I
It's not like
uploaded
that.
on your
It's-
computer, so our computer would.
The higher
Our
number,
computer didn't have a
the
DVD
harder it is
burner,
to get to yourself.
and then we got our new computer. Okay, that makes
I'm like,
sense.
It was
I am
so-
so confused, why?
It's
Kramer, I'm like you, I'm gonna
I
lose
can't think of
English.
Oh,
Yeah, so I took the practice ACT, just like an old
When
one,
it-
and I
slope is
feel like I
exponential.
bombed the science, and then I get the results back, and I was
The higher you get,
so that just
more
tells you
things
how I
get to
did.
that level.
And then the reading was really bad, and my math was my best one, which I figured it was gonna be. Math is easy for me. The timing is what killed me.
Yeah, I told you that.
Yeah,
Everyone
makes
knows
sense.
that.
I did.
Yeah.
Do you want a minute?
Yes.
Get the, at least the smell out of your mouth, it's Altoids too, so
Smell out of your
it'll take like 4.
Okay.
So he did that,
I take 5.
on Wednesday, and it's
No.
no.
Altoids are really. I like it.
Alright,
Okay, no, you get 1 more. You're not taking only.
alright, polyprotic, come on. Polyprotic, what does poly mean? Okay, so polyprotic acid is one that can give off more than, well, technically, we'll say more than one in this case. So technically, poly doesn't really fit very well here. But an acid with more than one acidic proton, it dissociates in a stepwise manner, which I stated, I think, at the beginning of this chapter, correct?
The first one's strong, and the second one would be a weak acid.
Yep. Okay. So here are 2 polyprotics. It's only going to give off a hydrogen one at a time. Okay. We know this is a strong acid. The conjugate of this is very weak. This is a weak acid, which means the next one's even weaker, and the next one's even weaker, and that's what this is saying. Typically for your polyprotic acids, what you get is each next step is weaker. And this should make sense because this guy is going to have a harder time giving off a hydrogen. Why?
It's fighting a charge.
And this guy is going to be even harder to give off its hydrogen because it's fighting an even bigger charge.
Yeah.
Make sense?
Yep.
Okay. So, typically for a polyprotic acid in water, only the first dissociation is really important for determining the pH. Because the first is typically a lot stronger than the second and the third steps, that even if you add the amount given off by the second and third steps, it doesn't contribute enough to affect your pH. Does that make sense? It's like saying, I have a weak acid, and we know water also gives off a certain amount of H+, but we don't ever add the water's H+, do we? It doesn't give off enough to make it important. Okay, so only the first step is really important when trying to figure out what your pH is. So, let's do this one. This one's a little bit of work here. I'm gonna throw up. Calculate the pH of a 5 molar N3PO4 solution, and then find the equilibrium concentrations of everything. What do you think we should do first?
Right.
Okay. I just didn't show water. Why? Not really that important. Okay, so could we figure out the amount of H+ given off by the first guy? How do we do that? Could we figure out the H+ concentration from this?
Yes.
Is that a hard question?
Yes, gets you the P. No.
I mean, they gave us the initial concentration. We know it's a weak acid. Wait, did they not give us the Ka value?
No.
Well, you have to find it in your book. Go in your book, here's what it is.
They know we can't know it.
Shush! Right there. Yeah? Now, why is it okay for me to not to completely ignore the ice table in this situation?
Because there's zero others.
Zero of the other stuff initially. It's a weak acid that isn't going to dissociate much. We know X is going to be really small. Okay.
You can do that for a strong or a weak acid.
Sure.
What if it's strong?
If it's strong, you just know that
That's the
completely
number.
dissociates. And
It's at 5.
yeah. Okay. So when we find X, do I get it or are you waiting for me?
It's 0.194.
Just go like that. So then we got to make sure with the 5% test. This one's actually close.
3.9.
Okay, so it's valid, but it was pushing the limits a little bit. Okay, well if you look at it, this Ka, that's a relatively high Ka for a weak acid. Okay, so it makes sense that this is going to dissociate maybe a little bit more than your typical guys. Right? Can we find the pH of this? Right? Okay, negative log of. And the reason why we can say 0.19 and don't have to do any more work is because we know this is an acid and not a base, right? And we also know that the second step and the third step of giving out hydrogens is considered to be what? And therefore negligible, right?
Oh, okay.
Right?
Sure.
Isn't that what we just, yeah.
I mean, I knew it was less. I didn't know how much less.
Well, that's what this was saying. Only the first associating step is
Okay.
important.
Got it.
Okay? Yep. Okay, this is where it gets a little bit more difficult, but we can still use kind of our, just what we know about equilibrium. All right, first off, we have enough information to find the equilibrium of fat. What is it? And how do we find it?
Well, the 5 minus the
Yep.
H plus.
5 minus the x, right? About 4.8. You confused? Anybody? Does that make sense? Okay. We also should know this. What is it?
The same. No, or very small.
It will be really small, and we already know it. What is it? 0.19. Because that, so imagine we did our ice table, imagine we did our equilibrium expressions. This is our x, right? We know the concentration of this is the same as the concentration of this. They're both the x's, right? All right, now you would also have to look up your Ka2 in your book. Here's what it is. 6.28 and your Ka3. Negative 13. Wow, that would be bad. All right? And your Ka value suggests that each additional step is becoming weaker. Okay? Now, we know the Ka2 is, we could do the equilibrium expression. Now, this would be your reactant, does that make sense? And you would just drop off another hydrogen from it. So your product would be removing a hydrogen from this. Still have our H plus. And don't we know both this and this? We know this, and we know this. Well, it's the same, right? Stop me if you're like, I'm not processing that. So slow down. So what you're gonna find is, if I plug in 0.9 here and 0.9 here,
Right. Wow.
yeah. So,
How concentrated is that?
yep. Your HPO4 2 minus concentration is just 6.2 times 10 to the -8. Now, does it make sense why we just put in 0.19 here?
Yeah.
It's actually probably a little bit greater than 0.19, but not much to affect much at all. Does that make sense? The reason why it might be a little bit greater is because technically this gave off a little bit, and then the next step gave off just a tiny bit more, but not enough to really affect this number if we were to round it. So we just leave it as 0.19. All right? Okay, A3 then. Okay, so now we're dropping off, that was an awful bracket. So now we're dropping off another hydrogen. So this is my reactant right here. You're still ready. You want me to slow down? What? Everyone understand that this is going to be my reactant for my third step? And when it gives off its last hydrogen, and again, same thing applies here. We just figured this out, and we know this. We can solve for this. Which ends up being this times this, which we said was divided by 0.19 should give us PO4 3 minus concentration. And it will be a really small number, and it should. It's pretty much not even there. Right? I mean, it's the third step. It's getting harder and harder to dissolve, or not dissolve, to react. It's pretty much not even reacting at all.
At that point, wouldn't the water get be stronger?
Yeah.
So-
And that's why we're saying that really the first step is really the step that matters much at all. Now this is for weak acids. Sometimes when you start with a strong acid, the second step can become important, which we'll get to. Right? We got 11 minutes. Questions before I move on?
Your concentration for the first two will be K and 1.
So you're saying what we got for X here gets puts back into here, is that what you're saying?
Well, like, I was thinking because there's 4 of them, I was like, how does K2 go to the third one, K3 to the next one? That's
So yeah, this would be Ka1. This becomes my reactant. Okay, and then it breaks down into with one hydrogen left, and then that becomes my reactant and breaks down to no hydrogen left. All right. Okay, so sulfuric acid is pretty unique in that it's a strong acid, but also has a second hydrogen that it can give off. Even though that's weak, it's actually a fairly strong weak acid, and so there is some stuff that we gotta keep in mind here. Do I have time to show both? Okay, I might jump down to the second one and do the second one. What this first one was going to show you is, I'm going to go ahead and just explain this and kind of walk you through what we would have done in the first one. It says in solutions more dilute than 1, the dissociation of this becomes important to solving the problem. What that means is when H2SO4 is less than 1, the second step, or the second hydrogen that's given off, is enough to significantly affect the pH. And this should make sense, because remember how we said the more dilute it is, the more it does what? Yes. Okay? So what this first problem was, is it was at 1, and I was going to show you how when you solve for the second step, it didn't have an effect. That makes sense? So you would have just taken, right, this is a strong acid, so you would have just taken negative log of 1, and that would have been your pH. Does that make sense? And you would, I was going to show you that when you do the second step of it, it gives you like 1.2 times 10 to the negative 2 or something, but when you take and round to sig figs, it still just gives you 1. Okay? However, when you have a concentration that's less than 1, now the second step becomes important. Okay, so quickly, the first step. Now what is this specifically for though? Because we didn't have to do this on the previous one. On the one where we just did the whole thing for.
Second step?
This is when you start with a strong acid that has, and it's actually only this guy, because it's the only strong acid that can give off a second hydrogen. Does that make sense? So this is this greater than 1, less than 1 concept is specifically for sulfuric acid. No other guy does this. Okay? Well, we know that the H plus given off by this is just what? Does that make sense? Because it's a strong acid. Okay? Now I want to show this. However, this is a little bit more complicated problem because both these aren't what? They're both not 0. Because we have some of this. Does that make sense? So we are going to do an ice table. Okay? Now, how much of this do I have? Everybody see that? Because this broke up to give me this, so both this and this are going to be the same. Okay, because this is 0, we're going to still assume it's going to shift to the right here. Minus x, plus x, plus x. I just do 0.01 minus x, save myself writing the times 10 to the negative 2. So, we go over here, KA2, and they give it to you, oh great, I gotta give you the KA2 again. You'd be able to find this in your book if it didn't give it to you, what is it here? 1.2 times 10 to the negative 2. It's actually a fairly strong weak acid. Alright, so now it's not x squared on top, is it? No. X and that. Now, we can check the 5% test, but I'm going to show you that it's not going to work. So I could remove this x, but I could also remove this x if we say that it's small, right? So, and when I get rid of this x and this x, what happens to these two numbers? Make sense? 5% test, just to clarify. Doesn't work this time, does it? Okay? So what do we have to do? Quadratic. Alright? Here we go. I probably don't have time to do, I'll just simplify this for you. You guys all know how to do quadratic stuff, so I'll just give you it in its standard form there. So that would be if you took this and you simplified it all out, got it in quadratic form. Right? And then when you plug into your quadratic equation, you will get and what is it obviously? This one, it's not going to be this one. Okay? That tells us, okay, what the x is. What would we do to finish this then?
Do the 101 minus.
Oh, it's not minus. So our pH is going to be the negative log of 0.01 is what we got from the strong portion of it, plus 0.0045. Right? Should give you 1.84 as your pH. Now let me just check what it would be if you didn't add the 0.0045. You already got it?
Negative log 0.01.
Yeah. So it's a significant amount, or enough to affect the pH that we need to apply it. So in this particular situation, what's true? It's very specific. It's just for a guy like this.
This is for strong acid associated splice.
Okay? If you have a concentration that is less than 1, you'll find that the 5% test doesn't apply. You have to use the quadratic. If it's 1 or above,
And this is what?
you can assume that the second step is what? Negative.
So you only have to do the second step for each of them?
When it's less than,
Yeah, so if it's less than 1, it shows up for you. That's the only case.
yeah. Well, unless you had
A different.
there's some weak acids where you might have to use a quadratic, if it didn't follow the 5%.
And do like the second step?
No, you
That's
probably
the
would
one.
never have to use the second, you would just have to do it on the first step. You aren't, for a weak acid, I don't think you're ever going to have to worry about the second or third step.